Welcome back. We're into our last little look at revising chemical change. And the thing we want to zoom in is on acids and bases. Now, acids and bases are a particular type of chemical equilibrium reaction. This is quite a big topic, and we're not going to have time to do everything because the stoichiometry that's linked to this has been done in other lessons, so we're not going to follow that. Also, recognize that stoichiometry is linked to titrations. So we're just going to focus on some of the theory that's taking place in acids and bases. So there are two main theories. There's Arrhenius theory and Lowry-Bronsted theory. You need to know these two theories. And I can almost guarantee you that one of these definitions is going to come up from one of the theories. So there are four things you need to know. What is an acid? What is a base? According to these two theories. So let me remind you that in terms of Arrhenius theory, an acid produces hydrogen ions. That's H+, aqueous, or we can say hydronium ions, aqueous. Now remember, a hydrogen ion is just a proton because hydrogen has one proton, one electron. It's lost the electron, becomes positive, so it's a proton. And that's going to become important in our next theory. The bases produce hydroxide ions. That's OH-. In aqueous, AQ. So remember the phase indicator? AQ stands for that. That's Arrhenius' theory. Anything that produces hydroxide ions is a base. Anything that produces hydrogen ions, when you dissolve it into water, is an acid. Guys, there are some exceptions. We can find things that don't produce hydroxide ions, but they're still going to be bases. There are some things that don't produce hydrogen ions, but they're going to be acidic. And so we need to be aware of that this theory isn't complete. It needed to be replaced or added to. And so Lowry-Bronsted came along, Bronsted-Lowry, sometimes reverse those, and they indicated the following, that an acid is a proton donor. There's a transfer of hydrogen ions. Those hydrogen ions, just the protons, and a base is a proton acceptor. Now, let's go and have a look at a reaction where we can see this happening. And the most important of these reactions is the reaction that takes place between two water molecules. It's also known as the auto-ionization of water. So have a look here. Auto-ionization of water is the reaction of water with itself to form hydronium, that's H3O+, plus hydroxide ions OH-. So in the auto-ionization of water, particularly said that this is at 25 degrees, and you'll see why in a second. The water molecule bumps into a water molecule. This water molecule donates a hydrogen ion. And if it has donated a hydrogen ion to this one, look over here. What's happened to that one, the second one? It has become a hydronium ion. And this one, which was hydroxide, it has become, this was water, it has become hydroxide. It has lost, this one has lost a hydrogen ion, and this one gained the hydrogen ion. And so that's the process. We would say this water molecule is behaving like an acid, and this one is behaving like a base, because it's accepting a hydrogen ion. Now, do you notice that in this reaction where we've identified water is acting sometimes as an acid and sometimes as a base, is actually in chemical equilibrium? Look, we've got the double arrow there. So water molecules on this side, and we've got ions on this side. And in fact, what we can do is we can say, so what is the role of the things in the reverse reaction? Well, this hydroxide ion, if it's going to go in the reverse reaction, it's going to be an acceptor of hydrogen ions, and that means that it will be the base, and in the reverse reaction, this will be the donator, so this is the acid. And there's a fancy name for this. In the reverse reaction, we call them conjugate. So that's the conjugate base, and that's the conjugate acid. And they form a pair. So what we need to recognize here is that the acid and the conjugate base form a pair. And here's the other pair. The base and the conjugate acid form a pair. Now, it's not that easy to see on this example. We'll come to another one. But I want you to recognize, because it's in chemical equilibrium, we can write a Kc expression for this reaction as well. But remember, we must only use those things that are in aqueous or gases. So that means that if it's liquid, we can ignore it. So if we write the Kc expression, it actually turns out to be this expression here, which is also called Kw. And it's known as the ionization constant of water. Ionization constant of water. And what's quite nice about this is at a particular temperature, and it has a value. Remember, that value is not going to change if the temperature doesn't change. So if the concentration of the hydrogen ion increases, for example, the product still has to be the same. So the hydrogen ion concentration increases, which means the hydroxide must decrease. If the hydroxide increases, the hydrogen ion must decrease. The product of the two have to always be the same. And so we recognize that no matter what, the Kw remains the same at that temperature. And this gives us an opportunity to define what pH is. In fact, pH is just a log equation of what we've just seen of the Kw. All we're saying is that at a neutral situation, the hydrogen ion concentration is equal to the hydroxide ion concentration, and that means that this will be equal to 1 times 10 to the minus 7. And if you multiply that together, then you'll get 1 times 10 to the minus 14. So by looking at the log of the hydrogen ion concentration, the minus 7 becomes 7. So it's actually quite intuitive in that respect. You can do lots of calculations on these. As we've shown, the water is an amphiolite. It's a substance that can react either as an acid or a base. There are other amphilites, but water is the most common one that we will look at most often. Here's the thing that we do need to get into. What's the difference between a strong acid and a weak acid? Well, a strong acid ionizes completely. It has a high concentration of hydrogen ions. And a weak acid will be one that doesn't ionize completely. It will rather prefer to stay as molecules, and only a low concentration of hydrogen ions. So the pH will generally be a bit lower. So the acid ionizes completely, and in this case, as I said to you, we're going to see that we've got, this is the acid, and that is the conjugate base. Notice that they differ only by the hydrogen ion. Now, for a base, the strong base dissociates completely, and we recognize something like sodium hydroxide forms hydroxide ions and sodium ions like that. So in acid-base reactions, final thing that I want to get to is that an acid plus a base gives you salt plus water. And that reaction and the balancing of those equations you need to know. But there's one other thing. When it gets salt and water, sometimes the salt can react with the water. We call that process hydrolysis. Please learn that definition because it's very important. You have to define hydrolysis, and we define it as the reaction of a salt and water. So when you come to a titration, the salt may react with the water, and the end point might not be neutral. And that's why we've got to choose the correct indicator. Guys, that's just been a quick revision of all the important concepts of the theory of acids and bases. Please do some more practice and make sure that you understand these are all related to chemical equilibrium as an example. So I hope you I wish you all the best for your tests and exams. Hope you found this useful, and I will see you soon. Bye for now.